Hi all, welcome to day 16 of Advent of Elixir. Today I'm going to show you how to make a transactional lock using the Erlang global module. In a previous episode that I'll link to below, I showed you what was difficult about getting counters to work. That in order for counters to work in a concurrent system, the retrieval and setting of the counter value must be transactionalized. So here I've implemented a naive counter with a tick function, and you can see that the store.get function and the store.put function are not transactionalized. What that means is that another concurrent use of this tick function can jump in between the get function and the put function, which means that these two separate concurrent runs of the tick function have the same count value. So when they go in to put the new count value in, they're going to wind up putting the same value in when in fact they should have put in values one after the other. So they should have been sequentially increasing count values. To exacerbate this problem, I've put a process.sleep function in here, which will sleep for 500 milliseconds, which will make this bad enough that we can trigger this concurrent access issue manually. In this video, what I'm going to eventually show you is another way to transactionalize activity across a cluster. So this is going to be a distributed transaction. Note that you really don't want to implement distributed counters using this technique. I'm just using a counter to illustrate the difficulty with access and modification race conditions in a format that you've seen below in the video below. Okay, so let's get to it. The thing that I want to really demonstrate to you is that this is a distributed counter by virtue of the fact that the store.get and store.put functions are able to set values in a common fashion across the cluster. The implementation details aren't important. For example, if you were running distributed Elixir, this might even be a database access. So let's go ahead and run advent.tick, and we can see it ticks to 1, and if I run it again, it ticks to 2, and if I do advent.count, on the right-hand side, it's aware that I've set the value to 2 from the left-hand side. And then I can do advent.tick on the right-hand side, and you'll see it increments to 3. And if I do advent.count on the left-hand side, it is incremented. It knows that the state has been incremented to 3. The problem then comes in when I try to run advent.tick at the same time on both cluster nodes. And what you'll see is that because these all triggered in alternating fashion, and there's a 500 millisecond sleep here, we wound up with both of them thinking that they had a new count value of 4, and both of them wrote 4 into the storage. So this is incorrect. One of these should have been 5 and the other should have been 6, but that's not what happened. So let's go ahead and fix that situation. This is exactly what we saw in the previous video, and the problem is that these need to be transactionalized. So how do we transactionalize something like this? Well, what we need to do is we need to use the global.trans function. This is a function that has 3 different forms: a trans2, a trans3, and a trans4. Trans2 is what I'm going to use, but note that trans3 and trans4 give you options that you can set that control exactly how the transactionalization works. In this case, I'm just going to use the default settings. So how does global.trans work? The first thing you need to give it is a token, and I'm going to describe how this token works in a second, but just bear with me. So we're going to fill this out, and then what I'm going to do is I'm going to wrap the content that I want to transactionalize inside of a function. So that'll look something like this. However, note that we've got a problem, and that problem is that this count needs to somehow make its way out of the lambda that we're using to wrap the function and back into the function that we are returning from. And so the way you do that is you will set self to this to be the self PID, and then we're going to go ahead and take, we're going to send the calling process a message. And this is how we're going to exfiltrate the count from this internal, this transactionalize function. And then we just need to trap that message. Receive, do. Okay, now let's talk about this token, which I haven't really gone over yet. This is a tuple, and it takes two values in the tuple. The first value identifies, using some sort of identifier, the transaction in a global sense. So what we want this to be is we want this to be some sort of constant value. For convenience, I'm just going to use the advent module name for that first value. What's important, though, is that any global.trans call will match on this initial value, and it will try to lock the execution of this function against any other transaction that matches that first value. In this case, I only have one function that is going to be used in this transaction, but what this means is that you can potentially transactionalize two completely different functions by using a same common identifier for the transactionalized path. The second value you need to pass into this token is an identifier for this particular instance in space and time for the run that is happening at that moment. And whenever you need to have a unique identifier in space and time in the Beam virtual machine, what you want to use is the makeRef function. I'm going to go ahead and illustrate what the makeRef function looks like right now. And it just gives you something called a reference, and that's just a unique identifier. You can see it's got a ton of data, and every time I run the makeRef function, it generates a different value. And these values are pretty much guaranteed to never be the same twice. Okay, so basically what we're going to do is we're going to run a transactional lock against this code here. And this is going to be the identifier for the transactional lock, which consists of the name of the lock. This should be global across all instances, and the current instance that we're running right now. Okay, so let's recompile the code on both virtual machines by resetting. We're going to check that these two nodes are connected, and they are. I've configured this so that these two nodes will always see each other and meet each other automatically when I reload the interactive Elixir shell. So let's go ahead and run advent.tick. And you can see that as before, we are ticking upwards, and if I do advent.count, it displays the value that we expect. If I do advent.tick on this side, advent.count respects the value. And if I do advent.tick on both of these sides simultaneously, you'll see that I am unable to get them to have the same number as I did before, because this the execution of the advent.tick function, or at least the core parts of the advent.tick function, is protected by this global transaction. I want to show you one more thing, which is how might I make it so that this count value, this count message is protected. So suppose a stray count message somehow makes its way to this function that's expecting to receive. Then what we're going to do is we're going to get whatever came from the stray count message and not from the one that got sent by this global transaction. I think that's a rather unlikely situation, but it's good practice to just make sure that the messages that we sent are uniquely identifiable. And this is how we do this. So what I'm going to do is I'm going to lift the makeRef above. So then what I'm going to do is I'm going to use that ref here. And the great news is that we can recycle this reference here. So the message is now going to be count a unique identifier and then the actual value. And here what we can do is we can pattern match on the ref variable that we have generated here. What's cool about this is we're reusing this unique identifier for both the transaction identification, the identification for that particular run of this transaction, as well as for the message that we're sending. And I think recycling these references is a pretty cool technique that if you get into more advanced Elixir content, you may wind up using. Okay, so I'm sure that in many cases you wish that you had some sort of way of transactionalizing execution in an Elixir cluster. I think a tool that a lot of people often reach for is a tool called Redlock, which uses Redis instance to create a transactional lock using the Redis database itself. You might also leverage your Postgres instance to do a transactional lock. But what's great about this is you don't have to have either a Postgres dependency or a Redis dependency in order to do a transactional function over an Erlang virtual machine. You can just use global.trans, and that comes in your Erlang standard library. Okay, that's all I've got. Hope to see you tomorrow for some more content.